Hello. Here we will talk about linear maps in the matrices. So here's some notations. We talked about vectors last time. Let's look at the set of all vectors of length n with coordinates in real numbers. This is a symbol for the set of real numbers, and n is just the measure of the length of a vector. So I'll be drawing them vertically to save the space. Coordinates are real numbers, and this bar is part of the set builder notation, which says that we can look at all collections of L real numbers written in the vector form. So the name for this set is the coordinate vector space of dimension n. And one key thing about these coordinate vectors, which we'll use many times, is the following. Any vector can be written as a linear combination. So we talked about operations on vectors, and effectively there are two kinds: addition of vectors and scaling and multiplication by numbers. And using this we can form sums of vectors with coefficients. They're called linear combinations. And now I'm going to write a particular linear combination representing an arbitrary vector in a unique form. So the vectors which will be combined in this linear combination will be of very special shape. They will be mostly zeros, apart from one position from one coordinate, which will be 1. And it's straightforward to see that any vector is a linear combination of such vectors in a unique way. The coefficients for this linear combination will be just the coordinates of the vector. So these numbers are called coordinates in general. And these vectors which we use are called basic vectors. This feature of coordinate vector space, where we have a finite collection of vectors giving us everything if we are allowed to use linear combinations, is a very central for linear algebra. We will use it again and again. So let's start using it now. And the thing we will be using it in is description of linear maps between coordinate vector spaces. So imagine that we have a map turning vectors of length n into vectors of length m. But not an arbitrary map, something called linear. And to be linear for a map, it has to satisfy certain conditions. And the first condition is that it is additive. If we have two vectors, v and u, and we can sum them up and then compute the value of our map, then the result should be as if we first mapped them into the second vector space and computed the sum there. So v and u are vectors of length n, those which we can feed in our map. The second condition is that scalar multiplication is also preserved by the map. Namely, it doesn't matter if we scale before doing the map or scale the result of doing the map. For any scalar, for any scaling coefficient, the answer will be the same, and these two properties together are called linear, being linear for a map. So an example, I would look at a map from 3 vectors to 2 vectors given by a formula. So there will be an arbitrary 3 vector which I can feed into my map. Its coordinates will be called x, y, and z. And then the result should be a vector of length 2. I will also write it as a column vector. and its coordinates is what determines the map. So my example will have the first coordinate computed by this linear function and the second by this function. What is crucial here is that the functions are linear themselves, meaning that they're just linear combinations of the coordinates we start with. And that will guarantee that the map we build out of these coordinate functions will be linear in this sense. So let's check. For linearity, we have to have first additivity and then preservation of scaling. Let's check additivity. Preservation of scaling will be similarly verifiable. So we have to imagine two vectors which we can sum up before doing the map and then do it in a different way. So let's call these two vectors x, y, z for the first, x prime, y prime, z prime being the second vector. So this is my v here, this is my u. And then I'm computing the sum of them before doing the map. And computing the sum is easy. The coordinates have to be summed. And now I'm ready to apply the recipe, which is this formulae, and compute the two vector. And the first coordinate should be the sum of whatever the first coordinate of the input is, plus twice the second coordinate, plus 3 times the third coordinate. That's the recipe. So my first coordinate is x plus x prime, twice the second coordinate is y plus y prime, and 3 times the third coordinate. And that is halfway through. The second coordinate is computed by this recipe, so I need to take x, which is a generic first coordinate, so it is now x plus x prime in this case. Need to subtract from it my second coordinate, y plus y prime, and then subtract the third. So that's what happens when we compute the value of this map on a sum of two vectors. Let's compare it with the sum of values. So now we just need to apply the formula to each of them and write the resulting two vectors. And then compute their sum. And that is easy. We just need to sum up the two coordinates we have in them. So we'll have x plus 2y plus 3z plus x prime plus 2y prime plus 3z prime for the first coordinate, and for the second we have x minus y minus z plus x prime minus y prime minus z prime. And now comparing the two, they're the same. They just differ by arrangement of terms, by the order of terms appearing. So if we just distribute 2 through the sum and 3 through this sum, we will have the same ingredients in each of the coordinates. So these two vectors are the same, and we check the first property of the linearity, and the second property is even easier, so I will not be doing it. Instead, I will be doing something more generic. I will prove that any linear map is given by this similar shape. It will be given by a procedure which turns a vector into another vector, perhaps a longer, perhaps a shorter, but in all the cases, coordinate functions computing my map will be linear. So let's just see how it is imposed on us from the expectation we have for our map that it is linear, and from the properties of vectors. So let's take a generic linear map, turning n vectors into m vectors, and let's imagine a generic input and vector or with some arbitrary coordinates called x's. What we can do with this vector is we could write it in the special decomposition and special linear combination form using these basic vectors. So that is before doing the map. And that is just because any vector can be written that good. It's just because the way we add vectors. But now we can turn on the special property of f, that being linear. And being linear means that we can simplify the value into, or write it differently as the sum of values. And these values will be only scaled coordinate vectors, basic vectors. And then each scaling coefficient can be pulled through. So the total effect after doing all these linearity transformations will be this sum. So instead of the first basic vector, we will have the value of linear transformation on the first basic vector scaled with the coefficient x1. And then with coefficient x2, we will have the value on the second basic vector, which will have the second non-zero coordinate, and all the way till the last, and there will be the value on the last of our basic vectors. So these values, they are some vectors of length m. And just let's write them more explicitly. So it's a vector of length m, and it has to have m coordinates, and I will be calling them a11, am1. So it will be my first answer for the transformation f, transforming basic vectors, transforming the first vector, and then the first is the second coordinate. It will be just showing that I'm transforming the first vector. All the way till the last answer, which will have coordinates 1n, mn. Again, each of those vectors is of length m, and then the number of the answer is recorded in the second index, and the position in the vector is the first index. So that's just a convention. And using this convention, we can now write the answer for our linear map in a more explicit form. So we will have x1 times the first answer times f of the first coordinate basic vector, and all the way till the last. And finally, we can rewrite it as just one vector, and what will be inside this vector, what the coordinates of this vector will be, there will be just linear combinations of x's. So the first coordinate will be the sum of first coordinates from all of the vectors we sum up. And the first contribution will be this coordinate times x1, so I just changed the order in the product, plus all the way through the product of this coordinate times xn. And as a function of the input, so the variable here is just this input vector, and these coordinates are what we can change. And as a function of these changing variables, we have a linear answer for the first, and it's happening all the way through the coefficients in these vectors. The coordinates of these vectors are just recording the coefficients of linear functions, which we will have to use computing the general form of our transformation. So finally, a new notation. Let's call this vector result of multiplying the matrix with the column vector of x's. So that is just the definition. That is just the new concept of a pairing of multiplication between a matrix and a vector. We can multiply a matrix with a vector if sizes match up, namely if the dimensions of this matrix are m for the number of rows and n for the number of columns, and then we have n rows and 1 column, so that is a special matrix of just 1 column. And the condition that we can multiply is that these middle dimensions coincide, and then the answer will be just that vector. So that is a product of a matrix of size m by n and an n vector, and it gives us an m vector. That is the first new really definition in this lecture, because everything else is forced upon us. Of course, linearity for the transformation is also an important definition. So to conclude what the matrix of a linear transformation is, we could compute the matrix of this transformation, for example. So to make it more industrial, let's just see what happens. So how do we read off this matrix from the shape of a transformation given by linear functions in each coordinate? We'll just collect the coefficients. So coefficients will be 1, 1 for the first column, 2, minus 1 for the second, and 3, minus 1 for the third. And another general recipe, which really comes from all this computation we did, is that a column in the matrix is the answer for the transformation on the corresponding basic vector. So the first column will be the answer on the first basic vector. The second column, the answer, the result of transforming the second basic vector, and all the way to the last column, where we have to transform the last coordinate basic vector and then put it as a column in our matrix. So that is another general recipe which will be very helpful. So maybe just a quick illustration of how this recipe is helpful. Imagine a transformation transforming vectors of length n into vectors of length n again. The easiest imaginable transformation of doing nothing. It's called the identity transformation, and it just takes a vector v and it maps it into itself. So what is the matrix of this? If we just follow this recipe, we have to transform the first coordinate vector and use the result as the first column of our matrix, but we don't transform with the identity transformation, so the first column becomes just the first basic vector. The second column again is not transformed second basic vector. And all the way till the last column, which will be the last basic vector. And the matrix will have a specific shape. It will be square n by n matrix, almost all 0 entries apart from the diagonal where we have ones. And that is what is called the identity matrix. But really we got it from this procedure, from computing the matrix of a linear transformation, on transformation of doing nothing. So that is it. See you later.